I want to welcome everyone to session number 1 of our first Ampere Developer Summit. I am Sean Varley, and I will be mediating this session. We'll start out with kind of a general topic. Today, we're going to really talk about efficient computing and the way that Ampere's cloud-native processors, we coined the term, just saying, are built to really run a lot of cloud-efficient code. And I'm going to kind of introduce today my panel. So I'm obviously the Chief Evangelist and Vice President of Business Development here at Ampere Computing. And I have with me today Kate Goldenring, Senior Software Engineer at Fermyon, and Dor Laor, from CEO and co-founder of ScyllaDB. And I'm going to have them actually do a little introduction of themselves just to get you guys started, because they've got a lot of good things to say about efficient computing and the workloads that go well on our processors. So I'm going to hand it over here to Kate to just do a quick introduction.
Hi, everyone. So like Sean mentioned, I'm a software engineer at Fermyon, where we focus on making it easier to run serverless WebAssembly, getting that started locally and then deploying it to your infrastructure. At large, I am an open source developer, and I come from a Kubernetes on the edge background. So I am co-chair of the Cloud Native Computing Foundation's IoT Edge Working Group. And then on the WebAssembly side, I'm really passionate about making it easier for people to get started with WebAssembly, and with that comes good documentation. So I lead the group that focuses within the Bytecode Alliance documentation there. And then in general, when I think about what I want to work on, it is software that improves the sustainability of systems. And so I'll talk a little bit about how WebAssembly plays a part there. And then outside of my work, I love to get outside. And so I volunteer teaching mountaineering courses out here in the Pacific Northwest. And with that, I'll pass it off to Dor.
Thank you. Dor.
Thanks, Kate. So I'm Dor. I'm co-founder and CEO of ScyllaDB. I'm engineering my roots. At Scylla, we develop a high-speed distributed database. It's also open source, and you can run it as a service. Scylla has a compatible API with Cassandra and DynamoDB, and it runs at 5 to 10x the speed. Previously, I managed engineering and was a second engineer in the KVM hypervisor project, and I managed it for 6 years. I love open source, and we like to contribute to open source and develop open source. And beyond that, I also do outdoor activities. I'm much better than a PhD level. I think PhD level probably doesn't sound great. I have a PhD in snowboard. But by my own university.
Very nice. Thank you, Dor. And I am very honored to be with you both today. And I share your enthusiasm for the outdoors, cold sports. And I just found out that Kate's going to be doing some cold water diving here in the very near future. So we've got some real adventurers with us. All right. I'm going to kick off today's discussion talking about efficient computing here. Really, I'm going to just do a quick introduction to Ampere processors if people aren't familiar with them. This is something that if anyone has ever engaged with us, they'll probably know by rote, but it does help to kind of give an introduction into kind of the features that kind of differentiate Ampere processors. So we kind of start out with what we call a cloud native processor, which is comprised of these main things, if you want to boil it down: single threaded cores, pipelined caches, and consistent frequency, meaning that all of the cores have their own private cache. They run to completion all of the processes that are scheduled on them by OSs, and they always do that at a very consistent frequency, core in and core out, so all the way up to the maximum number of cores you are running at the same frequency. And so this is very different from the x86 ecosystem. What this really does is give you a very linear performance profile. So we scale from 1 to n, and we do that in the same quantum chunks that allow people to get very, very predictable deterministic performance. Now you combine this with modern code practices, which is why I really have Kate and Dor with me here today. And what you'll really get is a recipe for efficient computing. Now, I'm going to talk about a little bit about kind of the future, because this modernization idea is an imperative, really. We are sitting in a situation in what I would say really human evolution, where we in IT really need to get busy. We need to think about the environment. We need to think about starting to save and design for power. We need to think about these things in a lot of different ways because of the real capacity crisis that is facing us as an industry. If I travel all over the world and I see this all the time, data centers are running out of space. They're certainly running out of power. And with AI proliferation kind of in the offing right now, really it's already there in hyperscalers, but as we look at AI proliferation across the world in many use cases, we need to kind of think about the fact that we have to start making room for the power that will be associated with processing AI. You combine that with some aging infrastructure, and it's really not very power efficient infrastructure, because essentially our competitors are the incumbents, and they're not very power efficient. You get all of that and the cost multiplicative factors in place, and you really kind of have a crisis. So what we're looking for is more efficient computing as defined by sustainable servers, cloud native infrastructure, and modern code practices. And that is going to deliver us a much better profile. So Ampere to the rescue, we actually can provide the industry with the densest container platform on the planet. And here's just kind of a CAGR, chart on the left showing the container density versus time over our platforms. And as I said, this is a scalable, predictable, and sustainable infrastructure. If you combine that with things like these efficient code practices, which we'll hear more of from Kate and Dor, optimized containers, kind of distributed execution, stateless is a big thing, serverless, of course, is a thing, and scale out practices, you'll really get this kind of effect that allows us to pack more processes onto efficient execution infrastructure from a compute perspective. You combine that with elastic orchestration and the ability to do power-aware provisioning, and we really start to kind of click on all cylinders to deliver efficient code practices. So I am going to hand it over here to Kate to tell us a little bit about some of these efficient coding practices with WebAssembly and Spin and her experience there at Fermyon.
Great, thank you, Sean. So some people might not be familiar with WebAssembly, so I want to take a big step back and talk about how the cloud has evolved in a series of waves. And then with each of these waves, multi-tenancy is increased. So the amount of applications, independent applications that we can put on a piece of hardware has increased. And to Sean's point, the density that we've been able to get with containers has been great, but there's still more to be achieved. And so before the cloud, we didn't really have any way of having multiple tenants on a single piece of hardware. Then came virtual machines, where we're virtualizing hardware, so I can take my monolithic application and place it next to a different person's monolithic application and feel comfortable. And with that came the advent of the cloud. Then came containers, which led us to create applications that have microservices. So I can break my application into more parts and scale each of those services independently. And each of those services can be isolated from each other as well. So now we can run maybe dozens, maybe 100+ applications on a single piece of hardware. However, each of these containers can take about a second to start up. So I'm not able to dynamically scale as much as I would like. And so I really have to be predictive about how much I need to configure, which means that I'm not always getting everything I can out of my hardware. So the 2023 SysDig Cloud Native Usage Report actually found that 69% of CPU and Kubernetes clusters was unused. And that's in part because containers is that underlying use unit, and we can't scale as predictably there. So then comes serverless, the idea that instead of scaling on the microservice level, I can scale on the function level. And in this way, I can be more precise about scaling and therefore only use resources when I absolutely need to use them. And so now we can run thousands of applications and functions on a single piece of hardware and know that those are still isolated from each other using WebAssembly. And so I want to mention a little bit about what WebAssembly is then. Its name is a bit of a misnomer. It did start in the browser, but you can actually run WebAssembly out of the browser now. But it still has those characteristics that made it so popular for the browser, namely that it's polyglot and cross-architecture. And so WebAssembly can be thought of as two things. One, it is a bytecode format, and the other, it's a WebAssembly runtime. And so when I say bytecode format, I mean you can take any language of your choice, whether it's Go or Rust or Python or JavaScript, and compile it down to a WebAssembly component. And this is that .wasm file that I now can run cross-platform and cross-architecture and cross-OS, whether that be Linux and Windows or ARM and AMD. And I can run it anywhere there's a WebAssembly runtime.
And Kate, this actually brings up a really solid point that kind of goes with that whole efficient computing thing, right? We've got a lot of infrastructure out there on the incumbent architecture, which is obviously x86. And if you're going to put in new, more efficient architecture like the ARM architecture, the Ampere systems, you're going to need to run on multi-architectures. And this is something that really helps with that.
Exactly. Once you start targeting WebAssembly, that frees you up to make the architecture decision that's most cost effective, most performance effective, power effective, and you're not locked into one architecture. And I want to talk a little bit also about how serverless is ideally the solution for us in the sense that we can scale on the function level and achieve higher density. However, the existing units we use for serverless have been a little bit prohibitive when we talk about the density story. So one of the predominant serverless units today is the micro VM. So a micro VM is what is the underlying technology of AWS Lambda, and their cold starts can be 500 milliseconds and more, which means that your application is actually waiting to get ready to execute for more time than it's actually executing. And what this means is that providers that use micro VMs, such as Lambdas, such as AWS Lambda, have to pre-warm all those functions. So they're actually using resources of your hardware before they're actually executing, which means you can't host as many of them. And that can be cost prohibitive. That's also has a sustainability side effect there too, of that you have to provision more infrastructure. On the other side of things, WebAssembly cold starts are less than a millisecond. And so we can actually we can instantiate in memory in its sandbox security model and execute that WebAssembly function in less than a millisecond. And we truly can scale to zero, which means we can put thousands of WebAssembly functions on my MacBook Pro, for example. And so WebAssembly, like I said, it was in the browser, now it's moved to the server, and people are curious a lot of times, how do I get started using this? And think that there may be a barrier to entry. In fact, there's actually a lot of open source tooling out there that is specifically there to make it easier to get started running WebAssembly. One of the ones I work on is called Spin, and it has an easy CLI experience for scaffolding an application and then running it locally. And then you can easily deploy it to a cloud provider or some sort of infrastructure to run it. We actually have SpinCube, which is also open source, which enables running WebAssembly next to your containers on your Kubernetes infrastructure, or you can run it on Fermyon Cloud with the simple Spin Cloud deploy. And now your function is ready to be executed and respond to requests. And so I want to end with a quick case study. And this goes back to Sean's question of, if I switch to WebAssembly, can I then choose the architecture that is most cost effective for me based on my cloud provider? And the Zeiss group actually underwent this experiment. They were finding their containerized serverless solution to be cost prohibitive. So they switched to using Spin on SpinCube. So they switched to WebAssembly, and they were able to reduce their costs by 60% while also maintaining performance. And part of that cost reduction was once they switched to WebAssembly, they could add in more Ampere ARM nodes to their cluster, and therefore reduce costs due to the cost of those nodes on AKS. And
Yeah.
Go ahead, Sean.
No, I was going to say that's such a great example because, I think this starts to get to putting it all together, right? And when you get into these cloud environments where you do have choice, and a lot of choice, out there now with multi-cloud and hybrid cloud and stuff like that, and these tools that you're talking about really kind of help ease that migration, between different architectures, different instances. And this kind of gets, I think, even to, a recent announcement by Uber, who has done this very thing. And and you'll be hearing from them later today, actually, that I think also backs up this experience, the ability to kind of get to a much more efficient architecture.
Yeah, and then just one thing to jump in there, besides being able to change your mind about your architecture, you also never have to do cross builds with WebAssembly. You just build it once, which means if you're patching something, you just rebuild it once and you don't have to worry about all those container dependencies too. You're just focused on your business logic. So that's another part of the sustainability side of it too.
Yeah, fantastic. Excellent. Well, I love that example. Thank you for providing it. Let's see. I think we'll kick it over to Dor now to kind of get us a little bit more perspective on scaling, really kind of linear scaling and some of those elements that go along with this architecture. Dor, I'll hand it over to you.
Thank you, Sean, and thanks, Kate. I just wanted to say that we use WebAssembly too, and we were fans of it. We use WebAssembly in the database for running user-defined functions. And again, it's polyglot, so the user can write in every language, and also whatever the language the server runs on, it gets compiled at runtime with WebAssembly. So we're fans of WebAssembly as well. Going to efficiency and on ARM and on this architecture, our database is also shipped as a service over cloud native implementations, and the network is the interface, so it's abstract away the hardware, and our users want to use the best of breed of the hardware, the CPUs, the networking, the instances of choice. So it's important to find out the best hardware and the best cost-effective it's possible, and it needs to scale both vertically up with the number of cores, and we'll speak about it, and also out horizontally as the workload continues. So this is just a snapshot from top with a lot of ScyllaDB threads in a very big server, how they run together. So Scylla has a unique architecture. Our goal is to scale vertically up as much as possible and only afterwards scale out. And we have a shard per core architecture. That means that we run one software thread on every hardware thread. So traditional architecture is threads and locks, like the puppies here. You can think about a plate like the chip, and the puppy like the software threads. And they all, it's pretty messy when you have threads and locks. On the other hand, on the right-hand side, if you have one process with many threads, as many as you have actually CPU cores, then we can just bind them together and scale up, and there's just no mess about lock acquisition, which is very costly, especially on bigger machines. The bigger machine you go, then the cost it will make. And we all about trying to be the most efficient, cost-effective solution. There are multiple advantages for having bigger machines. Even if you have like the same amount of cores in few large machines versus the same amount of cores spread across many smaller machines, it's better to use the bigger machines, because if your MTBF is fixed, let's say once a year, then if you have fewer machines, fewer failures. Maintenance is easier because you need to do rolling restart in an upgrade. So just rolling restart 3 machines instead of 30 machines. No noisy neighbors because you own the entire machine, and no virtualization overhead, and just less moving parts. So we have a rule, when you size, then first start to fill up the biggest machine you can, scale up before you scale out, and only afterwards. And our users normally do need to have more machines. The workload doesn't fit a single machine, but use bigger machines and smaller ones. And Ampere is a good selection because it allows you to do that. We tested it in practice.
But I want to pause you just once on that. Go back to that slide really quick, because I want to kind of hit something there with your scale up before you scale out, because I know you know a lot about this, and I think you can give a lot of your experience here. So one of the things that I think what we see, to just strengthen your point about scaling up, is that with the Ampere processors, we typically like to see our customers run at 80, 90% utilization, even maybe even peaking at 100%, because what that means is essentially you're using all the cores. And this is very different than the legacy x86 ecosystem, because it's not there's not a threaded environment here. So I'm kind of interested in your thoughts about that, because you have to obviously maintain sort of demanding SLAs when you do that, and I think that's something that you could probably give your experience on, from a Scylla perspective, because that's something that you guys really focus on.
Right, thank you. So we enjoy ARM's single hardware thread implementation, because it makes things homogeneous, and it's just easier to plan, and you don't care if you have another neighbor hardware thread to run along next side to you. That's number one. And we also have lots of utilization in terms of CPU utilization. It's a good thing. It's not a bad thing. Sometimes users get alert of high utilization, CPU utilization. No, it's actually a good thing. It's to put your CPU into action. And Scylla has a unique CPU scheduler, and it has prioritization among its workloads. So, for example, if you add a machine in order to scale the cluster, you need to stream lots of data to that other machines, terabytes of data. So we have a CPU scheduler that knows what your main workload is and prioritize it, while in the background, if you have spare CPU or I/O capacity, we run the other less important workload in the back. And this way, even though the machine is 100% utilized, and we also check that all of the cores are getting utilized equally, because if one core is utilized and the others are waiting, you're not utilizing the whole machines. And we see machines with 256 CPUs all consume 100% CPU, and that's really fantastic to see that.
Thank you.
Okay, so we put the linear scaling into test, and we wanted to see if we can compare clusters of 3 machines each. Each machine has different amount of processors. On the left column, you have the smallest machines possible with 4 vCPUs and 1 billion keys. Next to them, you have 3 machines of double the size, 8 vCPUs, and we also doubled the volume, and so forth until you go to the machine on the right-hand side, which is really big, 128 CPUs with 32 billion keys. And in terms of ingestion, how much time it takes to populate the entire data set, it's double for every machine. It's linear scaling. It's linear time, 4 hours to populate 1 billion machines with 4 vCPUs each, and workload which is 32 times bigger on the right-hand side with a 32 times bigger machines. It's all take linear scaling time, because Scylla is scalable, and also AMD is scalable, Ampere is scalable too. Lastly, it wasn't that hard to support another architecture with modern stack. It's in modern tools, and it's relevantly easy. So it's relevant. We test that regularly, and compilation time doesn't make us a lot more complicated. Probably 99% of the code is C++, and only a little bit of assembly. So it works pretty good together with GCC and everything else. And usually, like you'd expect some other problematic areas, like different disks, different NICs, and so forth. The CPU is not a problem. And actually, ARM itself is an advantage for Scylla, because it has a relaxed memory model. It fits Systar because we don't lock. We do the sharding per CPU. So it's efficient, no need to explicitly lock, and the lack of hyperthreads and linear scaling is very valuable. We also have a testimony of Expedia, and there are plenty of others who wants to get the best results from the best compute platforms and the best database as well. Thank you.
So we're going to go to Q&A. We don't have a ton of time for Q&A, but I do have a couple here up on the question and answer board, and we got one from Ronald that says, thread versus shard. This is probably for you, Dor. Each execution gets its own slice of the pie, but isn't this more about a scheduler?
So there are multiple schedulers. There's the OS scheduler that schedule software threads, and we pin every software thread to the hardware thread, and we bind them. And we also assign subsets of the memory and make it NUMA local for every such combination. We call it a shard. We also have a scheduler in the CPU, in the app layer, but that's separate. It's possible to read about it. Go to GitHub and C-star library. It has plenty of information about it.
Okay, thank you, Dor. We also have another one from Dave about the spin cube. So maybe, Kate, you can weigh in on this one. What are the scaling limits of spin cube, and have you really tested it on Ampere hardware before? And how did spin applications scale with higher core counts?
Sure. So we have, for testing scaling limits of SpinCube on Ampere hardware, one thing to mention is that SpinCube comes with multiple different executors. So the default open source executor is the containerd shim, which essentially means that instead of containerd executing container, it's executing a WebAssembly component, or a spin app in this case. What that means is you're somewhat limited scaling wise to normal Kubernetes limits of like amount of containers per node. So we haven't been able to stress test the architecture as much as we've wanted for that kind of testing. But we have done comparative performance testing of SpinCube on like response times for Ampere hardware, and comparing that with like AMD hardware. The issue we ran into that, which is related to kind of what Dor has mentioned of Ampere nodes being quite reliable, is that we weren't getting consistent numbers from the AMD side of things, part because of the virtual cores, and so that comparative testing wasn't as effective as we wanted. So something we want to do is try focusing just on one architecture, and that would be interesting to do with Ampere nodes and scale up there. And then even more so want to focus on the executor we have called Fermyon platform, which is a highly dense executor of WebAssembly. And in that way, we can put thousands on one node, and we really can stress each node. And we've done that with Fermyon Cloud's infrastructure, and we're able to put over 5,000 spin applications on an 8-core machine. So I would imagine we can get very high numbers there, and it'd be a very fascinating test.
Excellent. Okay, I think that is about all the time that we have for questions, but I do want to remind attendees, if you have a question for our panel or for future speakers on panels, you can stick them in the Q&A, and we do have a networking session at the end. Many of our speakers will be available at the networking session to weigh in on questions that you might have. It'll be a little bit more interactive, so I encourage you to also take advantage of that session at the end of today's proceedings. I want to thank Kate and Dor for joining me. I think this has been an excellent discussion, and I really appreciate your insights here and lending them to our audience.